When Niels Bohr proposed his model of the hydrogen atom, it correctly predicted the energy levels and atomic transitions. But the idea of circular orbits of the electrons was completely wrong. The development of quantum mechanics showed that the position, energy, and angular momentum of the electron in a hydrogen atom is predicted by a mathematical model called a wave function. Wave functions are three-dimensional mathematical functions that can be used to predict the spatial distribution of electrons in an atom. Here, positive values of the functions are shown in blue, and negative values are shown in yellow. The intensity of the color represents the value of the function, so you can get an idea of the spatial distribution of the electron in each orbital. Like the Bohr model, the n equals 1 level has a single wave function, which we call 1s. It has spherical symmetry, and the electron has zero angular momentum. The n equals 2 level has a spherical 2s orbital that's much larger than the 1s orbital, and has a region where the wave function has the opposite algebraic sign in the center. But it also has three 2p orbitals that are shaped somewhat like dumbbells. The p orbitals each have 1 unit of orbital angular momentum. The n equals 3 orbitals are even larger. There's a 3s orbital, 3p orbitals, and 5 3d orbitals. They have much more complex geometric shapes, and there are buried regions where the wave function changes sign. The shape of each wave function is related to the spatial distributions of the electrons in that orbital, and the square of the value of the wave function in any region of space is equal to the probability density of finding the electron in that region. However, the detailed motion of the electron cannot be measured due to the Heisenberg uncertainty principle. If we look at just the energy levels, we can see that the 2s and 2p orbitals have the same energy in the hydrogen, and all one-electron atoms like helium+. Likewise, the 3s, 3p, and 3d orbitals all have the same energy. This is what makes the emission spectra of hydrogen so simple. The graphic here illustrates that when an electron drops from one of the three 2p orbitals to the 1s orbital, the difference in electronic energy is emitted as a photon of vacuum ultraviolet light, having a wavelength of 121.6 nanometers. This is called the Lyman alpha transition. In atoms with more than one electron, like helium, the situation is more complicated because the electrons partially shield each other from the positively charged nucleus. The three 2p orbitals have the same energy, but that energy is higher than the 2s orbital. Likewise, 3p orbitals have a higher energy than 3s, and 3d is higher still. The 4s orbital has just slightly lower energy than 3d, but 4p is higher still. Helium has 2 electrons, so we put them in the lowest energy 1s orbital, so the electron configuration is 1s2. Lithium has 3 electrons. Each orbital can hold a maximum of 2 electrons, so we put the third electron into the next higher energy orbital, which is 2s. We write the electron configuration in a shorthand that indicates the configuration of the next smaller inert gas, in this case helium, and the configure of the remaining valence electrons. Beryllium has 4 electrons, so its configuration is 2s2. Boron is next with the configuration 2s2, 2p1. Then carbon comes with 2s2, 2p2. We show the configuration with 2 unpaired electrons because that configuration is slightly lower in energy than pairing the electrons in a single orbital. Nitrogen has 3 unpaired electrons and a 2s, 2p3 configuration. For oxygen, we must begin pairing the 2p electrons, and the configuration is 2s2, 2p4. Fluorine is 2s2, 2p5, and neon is 2s2, 2p6. This is a very stable electron configuration because the n equals 2 shell is now completely full, and there are no extra unpaired electrons. As a result, neon is an extremely unreactive or inert gas. In contrast, sodium has 1 extra electron, which goes into the 3s orbital. This makes sodium extremely reactive. We keep filling orbitals to get the elements magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and finally argon, which has a very stable 3s2 3p6 configuration. Potassium is next, and like sodium, it's very reactive. The extra electron goes into a 4s orbital rather than the 3d, because 4s is slightly lower in energy due to the shielding effects mentioned earlier. Calcium is 4s2, and then we start filling the 3d orbitals, doing it in a way that maximizes the number of unpaired electrons in the 3d shell, as we did with 2p and 3p shells. Vanadium, for example, has a 4s2 3d3 configuration. When we add one more electron, something unusual happens. It turns out that a half-filled 3d shell is particularly stable. So an electron moves from 4s to 3d, giving chromium an unusual electron configuration of 4s1 3d5. Adding 6 more electrons gives zinc with its configuration of 4s2 3d10. And then finally we begin filling the 4p shell. Germanium has the configuration 4s2 3d10 4p2. This process of adding electrons to orbitals is called the Aufbau, or building up principle. It has 4 basic rules. First, fill the orbitals in order of lowest energy to higher energy. Second, there can be a maximum of only 2 electrons per orbital. This is called the Pauli exclusion principle. Third, for any set of degenerate orbitals that have the same energy, the lowest energy configuration is the one with the maximum number of unpaired electrons. This is called Hund's rule. And finally, half-filled orbitals are especially stable, so sometimes a 4s electron will pop over to the 3d shell, as in the case of chromium atoms. With the aid of modern supercomputers, we can now calculate the properties of hydrogen wave functions, or orbitals, to a higher precision than we can measure them experimentally. This is an impressive feat. But for many electron atoms, the motions of the electrons and the nucleus are so complicated that our understanding of them is still largely qualitative, especially for heavy atoms, where relativistic effects complicate the picture. Nevertheless, this qualitative picture is useful for understanding the bonds that form between atoms to make molecules, compounds, and materials. And our ability to make accurate and predictive models of their properties improves every year.